and share my screen. So this while I figure out who called me. This is an amazing video. I always show this to my students who reach cardinality unit. So watch this.
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now, an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
That's it. I'm a big fan of cardinality. Some of you probably know already.
Is that a fresh with the press? Absolutely. In the beginning, I was
This is why I calls it. Yeah, I am a big fan, huge fan of cardinality because, well, it's what's going on because it's really interesting and mind blowing. It is mind blowing. I think I used the correct word. Um, why? So a few hundred years ago, when Cantor discovered these different types of infinity, they actually are different. None of the mathematicians believed him. So he mailed his paper about this to some famous mathematician at the time, and they all just threw it out in the garbage bin because everyone's like, this guy is crazy. Well, he was actually crazy. Cantor was suffering from severe mental disease while he was discovering this. Um, so basically, the thing is, nobody believed him. Okay, no one believed him. No one, everyone's like, this is bullshit. How can you have different infinity? Infinity is just infinity, right? Until another mathematician also discovered this, and people went back and looked at the paper and they were like, oh, it's actually true. So my point is, it is it is new. Okay, it is new. It is mind blowing. So even if you don't get it at the first, it's okay. Think about the famous mathematician. At the beginning, they didn't believe it either. They didn't understand it either. So it's okay. It is hard, but I think it's really fun. It's really interesting. Imagine those infinite hotel. Next week we will talk about those. We will talk about um, countably infinite and uncountably infinite. And we'll talk about how natural number and real number they have different cardinality, and we'll talk about even we have bigger infinity than real number. So cardinality of real number is it's not the biggest one. We can have even bigger one, and even bigger one. So we'll talk about those. We will also talk about Cantor's diagonalization argument, which is one of my favorite proofs. I love it, by the way. Those are not for this week. This week, we will talk about function composition and we'll move on to cardinality just a little bit, and next week is more cardinality. And because each of the questions I prepared are super long, so I split them into two parts again. The first part, which is done already, was in my last tutorial. In my last tutorial, we finished example 1 and 3b. So this tutorial we will do 3a and 2. 2 is a hard and long one. It's gonna take a while. Okay, so before everything, let's look at this function composition. I hope by this time you know what's composition of two functions. because, well, you've had your calculus. Right? Do you have another one this week? Is 135 test this week? This Friday? Tomorrow? Yeah, yeah. I did record my last one because I know I'm not gonna finish all the questions in one tutorial. Like I knew it because all the questions are super long. So yeah, it's recorded. I will post it after this tutorial. Do I have another tutorial after this? Oh, nice, nice. So it will be posted after this tutorial. So we'll do the other two questions. The second one is super long, so it's gonna take a long time. Anyway, hopefully by this time you know what's composite function already, so I'm not gonna go over that. Instead, we'll talk about some propositions. The first one is a composition of two injection is an injection. I think this one is proved in your course notes, so you can use it directly. 2, 3, 4, not proved. You can use them directly if the question is not asking you to prove it. However, if the test or quiz question is basically asking you to prove them, then you cannot use them directly. Okay? That's very unlikely to happen because, well, for those you can just search it up. Pretty easy to search it up. Anyway, you should know all four. You should know the composition of injection is injection, composition of surjection is surjection, composition of bijection is bijection. And if from A to B, D from B to C are two bijections, then the composition, the inverse of the composition will switch order. Okay. And also you should know that the inverse is also a bijection. Because, well, inverse of a bijective function is also bijective. Anyway, let's do 2. 2 is really low one. So the question themselves are not hard, but to get to there, like how do we come up with everything? That's what I'm aiming for, to explain everything. That's gonna take a while. So I will try to explain and you can ask question in the chat. Try to answer each other first. And when I'm done, I'll answer questions. Otherwise, we will not have enough time to do everything. Okay, so instead of doing the question first, I'm gonna start with what you should know. What you should know is, so I'm gonna write this down. So there is something in your course notes that says, if G compose F is injective, then F must be injective. So this is from your course. So the formal proof is in your course notes. Proof in course notes, which means you can use it directly. But I will explain why it's true. Okay, we'll have a short explanation. So I said if the composition is injective, then F must be injective. Why? So let's suppose F is not injective. Suppose F is not injective. What does it mean? It means that there exists a 1, a 2 in, let's say, in A. So by the way, let's define it first. So let's define F is mapping from A to B, and G is from B to C. So that means there exists an A1, A2 in A, such that, by the way, A1 and A2 are not equal. A1 is not equal to A2, but F of A1 equals to F of A2. So that means we have two things mapped to the same thing. So what does that mean? think about this. So two things map to the same thing. So this is your domain, this is your codomain. You have two things mapped to the same thing. So it's not injective, right? So this should be pretty clear. So that means that we have two different input mapped to the same output. So let's call it B. Then B of f of A1 equals to what? Equals to G of B. Would equals to B of f of A2. What does that mean? That means G compose F is also not injective. So this is a contradiction. You see? Does this make sense? Why it has to be injective? Oh, the proof is in the course notes, but I want to show you why. So this would answer number 4. Why? Because we know that if one of them, if my F is not injective, then my G composed F is also not injective. And so this is impossible. It follows directly from the above. So we solved the fourth question. So far, do we have any question? Did I lose everyone already? What's going on? There are so many of you here and nobody said anything. Make sense? Yes? No? Makes sense. Okay, cool. Next. So we talked about F. So we know that, well, if this is injective, then F must be injective. But what about G? Does G have to be injective or no? So think about this. So my next question is, we use another color. So question, what about G? Does G have to be injective or no? So let's suppose it's not injective. And see if it works. Suppose G is not injective. We know that F has to be injective, right? So we know F has to be injective. So that means let B1, B2 go from B. B is what? B is the domain of G. So I picked two elements from the domain of G. If B1 is not equal to B2, what we can have, because it's not injective, that means G of B1 equals to G of B2. So this means G is not injective. So what do we know? We know that B, so here, B is from B So it might be an image of F, right? Might or might not be, we don't know. Might or might not be. Let's say if B1 equals to F of A1 and B2 equals to F of A2. Okay, this is my assumption. I suppose your image of F. A1 does not equal to A2 would imply that G composed of F of A1. So let me write it in this way. G composed F of A1. So it's more clear. So this will be G of B1 would equals to G of B2, right? Because they're equal. And B2 is G of F of A1. What is this? This is contradiction. Why? Because this is telling you decompose F is not injective. So this is a contradiction. Contradicts decompose F is injective. So what went wrong? What went wrong? This is a contradiction. This is true. This is true. So this went wrong. That means at least one of the B1 is not in the image. So what does that mean? At least one of the B1 is not in the image means that F is not surjective. So F is not surjective. So if we want B to not be injective, so then we want F not be surjective. Okay, does that make sense? Now we can solve the first one. So we want G to be not injective. So what do we know? What do we know? So now I need the counterexample. What do we know? Not a counterexample. We need an example. We know that one, I want my F must be injective. So we want injective F not injective G. And I want my F not be surjective. Okay, so how do we come up with a one? So let's pick something. So let's let G be not an injective function. So let's let G, I pick something that's not injective. It's better to use piecewise function here because you're doing F first and it's not surjective. So you want F mapped to part of G. So if you use piecewise function, you want F to map to one piece of it. Okay, does that make sense? So your F is not surjective. You want to map to one piece of G of X so that this piece is injective. Does that make sense? I'm not sure if that makes sense to you. So that the whole thing is injective. The image of F is domain of G. Yes. So the image of F is like part of your piecewise function, and this part is injective. Then the whole thing will be injective. So I want to define a piecewise function such that part of it, the one piece will be injective, but the whole thing is not injective. So a good one is F, if F is greater than 0, sorry. So let's let this be like this. Let me use purple. Okay, and then the other one could be any number. So let's let it be, I don't know, be 1 if x is less than or equal to 0. So my G is obviously not injective. is not injective. Now look at my F. I set my F. First of all, it has to be injective. Second, it's not surjective, so I wanted to map to this. So I wanted to map to 0 to infinity. So give me an injective function that maps to 0 to infinity. Oh, by the way, I'm doing R to R, sorry. I should define the property. It's from R to R. So this is not injective. What about my F? R to R defined by, what do we want? Square root of X, but square root of X has 0 in there. Here I don't have 0. I want it to be 0 to infinity. E to the X is a good one, right? Is it? F of X equals to E to the X. Right, so thus in this case, it's injective, it's not surjective, and it maps to this piece. Then so you can check, C compose F of X would be T of E to the power of X. And this is greater than 0, so it's just itself. So it's X itself, so it's E to the power of X, which is injective. Does this make sense how we came up with a counterexample? I mean, this is not a counterexample, this is just an example. Does this make sense how we came up with the example? We need one more page, by the way. Make sense? No? Who is texting me? Oh, I got no feedback again. What's going on, guys? What's happening today? The example part? Okay. So basically, look at those 3 conditions. So to come up with an example for this, I know F must be injective. G is not injective. And I want F to be not surjective. So basically you're doing F first. Yes, so we want F that maps to the injective part of G so that the whole thing is injective. That's why I'm using piecewise function. Okay, cool. Really bothering me. Mute for today. Okay. Now I'm good. So next, we talked about injective. So let's talk about surjective. Starting with something you should know. If G compose F is surjective, then C must be surjective. Okay. Again, I'm gonna use the same thing. I'm gonna use AB and BC. Okay. 2, 2, 1, 1. What is this? This is not a proof, it's an example. So I'm saying it's possible, so and I gave an example. Wait, why do we wait? Yeah, I'm showing it's true. For the first one, yeah, it is true. It's possible. Yeah, give an example, satisfying the condition, or prove it does not exist. So I showed an example. Anyway, this the proof is not in the course notes, so I'm gonna briefly talk about why it's not a formal proof. So the following is not a formal proof. It's just showing you why, okay? If I don't write the sentence, people will think this is a formal proof. It could be if you add some justification, but we don't have time for that. So notice that, what do we notice? Notice that C composed of F of A. What is A? A is a domain, right? So G composed F of A equals to G of F of A. And what is this? This whole thing is the image of G composed F. And this whole thing is the image of F. You see? And what do we know? We know the image of F is the subset of codomain of F, right? You remember? F of A should be a subset of B. Okay, because of this, we know that this must be a subset of G of B. Okay, and similarly, this will be the image of G. And the image of G should be a subset of the codomain of G, which is C. So this is what we have. Then G composed F being surjective, what does that mean? If G composed F is surjective, that means image equals to codomain, then G composed F of A would equal to C. We don't know if F is surjective or not. F and G are just random functions. So this is always true, no matter if they are surjective or not. Because this is subset or equal, could be equal, okay? So since we want this to be true, we know this is already a subset of C. That means you want C to be what? You want this direction to work as well, right? Because you want them to be equal, you know this direction is always true. So since you want them to be equal, that means this direction has to be true as well. This means C must be a subset of G of B. What does it mean? This means that C is surjective. Does that make sense? So we know this is always true. You want them to equal, then that means this direction has to be true as well. If this direction is true, then G must be surjective for it to be true. Okay? So this solves 2. Number 2 is basically asking you, can you have them be surjective but G not be surjective? No, this is impossible. Okay, so this is impossible. Impossible. It follows directly from above. Okay, any question? Cool. So starting from here, A is a domain of F. So this whole thing will be the image of G composed F. F of A is the image of F. And we know that the image is always a subset of the codomain. right? So that means f of A is always a subset of B, which is a codomain of F. So that implies that G of B, so this must be a subset of G of B because this is a subset of B. Okay? And G of B is the image of G. We know that image have to be a subset of the codomain, so it must be a subset of C. However, now they tell us G compose F is surjective. Surjective means image equals to codomain. So that means this image has to be equal to the codomain of G compose F. However, if they are equal, then this direction must hold true as well. So that means C must be a subset of G of B, and G of B must be a subset of this, and so on. So that we know that for this to be equal, this must be true. If this is true, then G must be surjective, because this means that they're equal. So the domain equals to the image. Okay, so if G compose F is surjective, then G must be surjective. That means this is not possible. So since we talked about G, my question is, what about F? Does F have to be surjective as well? So think about this. So again, we do the same thing. We suppose it's not surjective. Maybe we can reach a contradiction. So suppose F is not surjective. We know that. We know G must be surjective. So what does it mean? This means that F of A is not equal to B, so they are not equal, but G of B equals to C, and G compose F of A, which is G of F of A equals to C. So look at this and think about what does this mean. So look at this and this one and this one. So this is not B, this is not B, it's not B, but G of B equals to C, but this is not B. So what do we need it to be? What does it mean? Think about this. What does it mean? No, not necessarily. So it's not we said it's not surjective. So think about this. This is A. This is B. This is C. So this is F. This is G. So my F of A is not B, so it's part of B. So let's call this part F of A. Okay, this part is F of A, and then this part itself. Okay, only taking this part itself, it's gonna map to everything in C. It's not the whole thing. The question is right here. What about F? Is F injective? So think about this. Yes, G is not injective. So G might not be injective. Hold on, let me think. Those map to here. And then only this part can map to a whole thing. So you might have something here map to the same output as well. Yeah. So G is not necessarily injective. F is we already suppose that G can be injective and it could be injective, could not be injective. It just doesn't really matter. Okay, so let's think about how do we do this. So I want the not surjective function. So this one, to come up with a counterexample, which one is it? 3. So for this one, you want to come up with a counterexample. How do you do that? What do you want? What do you want? We want G compose f of x equals to x. This is telling you, try to use inverse. Use inverse functions. So one of them is f, the other one is f inverse, something like that. So one of the example we can have is let f of x. Oh, again, I need to define it properly. Let f be R to R via f of x equals to e to the power of x. This is not surjective. Okay, and I'm gonna use what do we want again? We want f to be not surjective and decompose f is surjective. Okay, so let G also from R to R. How do I define my G? G must be surjective, that's correct. And not injective. So you want it to be surjective but not injective. And you want it to be inverse. So I'm gonna define G of x be ln x. So I'm gonna map. So this is gonna map to this part. So that if you use this, it's gonna go back to x. So that's gonna be x is greater than 0 because this maps to greater than 0. So that's gonna do this. And the other one, you can pick any number. So let's say ln x could be anything. So let's say 1 if x is less than or equal to 0. 1 decompose f of x is d of f of x. F of x is e to the power of x. E to the power of x. So that's gonna be ln of e to the x, which is x. And this is clearly surjective. The reason I use this is because I don't want to prove it's surjective. If it's just x, it's clearly surjective. So you want to use something that's you can easily see that it's injective or it's surjective, so that you don't need to provide a proof. Okay, that's the whole reason I wanted to be mapped to x. because this is greater than 0. Okay, so from above we can reach a conclusion that if, oh, by the way, I should use this, you cannot use it directly. Because it's not in the book. What about if x is less or equal to 0, then it maps to 1? Anyway, you cannot use it directly, but we can reach a conclusion that if G compose F is bijective, then F must be injective and G must be surjective. Okay. Question? Someone just has your camera on. Too excited. Both F and G are not surjective? What do you mean? This is surjective. This is surjective. It's not injective, but it's surjective. Law of X, it goes to everything. So it looks like this. It's negative infinity to positive infinity. G has to be surjective. Well, you care about the domain. It's just in function composition, the domain depends on the image of this. Okay. Yeah. Oh, move on to cardinality. We spent too much time on this. It's a long question. Okay. Go up. Okay, cool. Cardinality, quickly talk about this. So cardinality, we say two sets have the same cardinality if there exists a bijection between them. So if you want to prove two sets have the same cardinality, you need to construct a function f that maps from one to another. Doesn't need to be A to B, it can be B to A as well, okay, doesn't really matter. But you need a bijection F such that A maps to B. And then you need to prove F is a bijection. So look at this, you should already know that your F, the easier it is, the better it is. Otherwise, you're gonna spend like an hour proving it's a bijection. Okay, so you want some simple function, the easier the better. Okay, you don't wanna get a monster, a beast to make your own life harder. So what do you want to avoid? You don't want absolute value, right? You hate absolute value, so try to avoid those. What else do you not like? You don't like square root, so try to avoid those as well. And because if you use those functions, you need to prove it's a bijection. So that's gonna be really hard for you. So don't make your own life hard and don't make the TA's life hard. Exam, I don't care. I'm not marking next. Oh, actually, I'm not marking the quiz either. So do whatever you want. Do whatever you want. But if you are my students, please don't use really hard example in your problem set, okay? Because I don't want to read that. Anyway, back to this. I did part B in my last tutorial, so we'll do part A. So they did an easy question on composition and a hard question on cardinality. So you do a hard one on composition, easy one on cardinality. So let's do the easy one. It's a classic one. Copy. Yeah, see how much space we use to prove that. So now I want to prove those two sets have the same cardinality. The question itself is not hard. It's just we spent a lot of time proving the bijective thing. So this is a function, which is pretty simple, but proving it's bijective took a lot of space. Anyway, let's do this. So I want to show those two have the same cardinality. So I want a bijection between them. For me, what I usually do is for intervals, to prove two intervals have the same cardinality, I always start with drawing them out. So let's draw them out. This is your A. And it's this. This is my A, okay? And I'm gonna draw my B. You'll see it's really helpful later when I finish drawing. B is 6, 7, 8, 9. So go a little bit further to 9. And it's 3 to 4. So 3 to 4 and 7 to 9. This is my B. Now, I want to map from A to B. I want to map from this to this. So what I'm doing, so think about this. I want to map from this to this, and it's a bijection. So I want to do something such that A and B look the same. Does that make sense? I want to do something such that A and B. So after you do your after you apply the function, your A and B should look the same. So by observing that, I saw that, well, B has two pieces. So I'm gonna split my A such that it has two pieces as well. So my first step is I'm gonna split it into two pieces. So I'm gonna do this. This is not too obvious, so let's use this color. So I'm gonna split it into this piece. So this is my first piece, which looks exactly like this. And I have another piece from here. So we can take this point and go from here to here. So that's my second piece. So this is my rough work, by the way. So let's do some rough work and see what my function would look like. So I'm gonna write A as 1 to 2 union 2 to 5. Does that make sense, my first step? So this is my A now. So my point is I want to map this to this and this part to this part. That's my goal. Okay, so my first goal is map. I want to map 1, 2, 2, 3, 4. How do I do that? What do I need to do to map, to change this to this? Anyone? +2, right? Right? You just need to shift this 2 units here, right? So we just need to shift it 2 units to the right. So you wanna change it to here. Then it looks the same as this. So that's gonna be x plus 2. Simple? So far? What about the second part? Second piece. We have from map, well, I wanna map 2 to 5 to 7 to 9. So first of all, what is the length of this? How long is it? How long is this part, this piece? 3. What about the lower part? What is the length of this? 2. How do I change something that's length 3 to length 2? So that's my first step. A, change 2, 5 to length 2. How do I do that? Exactly, you divide by 3 and times 2. So that's gonna be x over 3 times 2. Okay, not -1, because -1 you're basically shifting it to the other side. If you do -1, you're shifting it to here. But that's not what you want. You wanna what's it called? You wanna compress it, right? So if you think of it as like function composition, you wanna compress it, not switch it. You don't wanna shift it left or right. You wanna compress it. Okay? So, but after we do this, what do we get? So what is my new interval? What does this give to? So 2 over 2 times 2 over 3 is, this becomes 3 to the, no, 4 over 3. And then 5, so that's 10 over 3. Right? So this is what we have. So if you do this, that's 10, 4 over 3. How big is that? So the new one becomes something like this. So this is a new one. So around this. So after you shift it, this part is your new interval. Okay, it has length 2 now. So now they both have length 2, but you want to shift this to this. You want to move it to the side. So what do we do? Oh, this is round bracket. 2, 7, 9. What do we do? Add how much? What is 7 minus 3 over? What is that? 17 over 3, exactly. So we need to add 17 over 3. So times 2. 17 over 3. Okay, after you add that, that's gonna be, Ronnie, no. So this is gonna be your final one. That's gonna shift it to here. Okay, so they have the same one. So here is my formal answer. So my answer is proof. Let F mat from 1 to 5, 2, 3 to 4, union 7 to 9. Defined by a piecewise function f of x equals to x plus 2 if x is in 1, 2. And it's 2x over 3 plus 17 over 3 if my x is in 2 to 5. Does that make sense? And now you need to prove it's a bijection. which you can do it yourself, I believe. Okay, do it yourself. Do it yourself. Now, any question? Well, when you prove it, of course you need to split into cases. Okay, so you need to consider. So, for example, if f of x is in 3, 4, then you have the first case. If it's in 7 to 9, then you have the second case, and then everything else will be easy. Next quiz is in next month, so not anytime soon. Okay, do we have any question? When will you upload the video? After we are done. Yeah, after we're done with this tutorial. Whenever they send me an email said the video is ready, I'll upload it. Don't worry. Okay, so let's stop here. It's a long tutorial. See how many pages I have. I have 6 pages. This is a huge tutorial. Okay, I will see you guys next week. Bye. Bye bye. Bye bye bye. Everything will be up on YouTube. Bye bye.